So our next speaker is Professor Holger Frey. He's from the Department of Chemistry, so he's doing those things that I never understand, so as well as all the other people do around me, but that's complementing. And he's talking today about PEGs and making the non-immunogenic universal PEG alternatives obtained by isomerization the PEG structure. Holger, the stage is yours.
Thank you very much, Volker. Yeah, it's a pleasure to be here, and it was always a goal of mine to be able to give a talk at a conference like this, because we are a chemistry group, actually, polymer chemistry. But, well, to calm you down, I will keep the chemistry as simple as possible today. It's about PEG. In the course of the talk, I will explain what rPEG actually means. It's a little bit cryptic, maybe, at this point. Except if you've already looked at the posters of some of my co-workers, whom I acknowledge very much. It's a great team, and it's a pleasure working together with all of them, and they are actually all here. Also Rebecca and Philip on the left side, two excellent postdocs who came up with this idea together with me, and only person who's not here is the lady in the middle, Verena. And I also have to acknowledge the ERC for an advanced grant, as well as, of course, our CRC 1066, on nanoparticles for cancer therapy. Well, you all know what PEG is, and if you look into the proceedings of this conference, you see that PEG is mentioned 321 times. So apparently it's important. And then you take a close look, and we all know PEG has this wonderful stealth effect, which is like, you know, Harry Potter's cloak, invisibility cloak for nanoparticles and all kinds of entities. And a PEG is safe and non-problematic. But if you take a close look, and this was also, of course, addressed by several speakers, including Johannes yesterday in his great lecture, a certain percentage of individuals do have trouble with PEG because they have a high level of anti-PEG antibodies, and this can lead to polyethylene glycol immunogenicity. And you see even the mass vaccination, which we've seen in the last 3 years, which was the biggest success of nanomedicine, of course, has led to a higher level of anti-PEG antibodies just by vaccination. So is this a problem or not? It appears it is a problem for a certain percentage, maybe 5, 6, 8% of the population. But we also, many of you know the ABC effect that comes with this. So maybe in the future, the PEG-related medicines will be less efficient than they should be. How does this come? To me, as a chemist, PEG is like a wet garden hose, basically. Yeah? There is nothing specific. How can antibodies interact with polyethylene glycol? And there are two really important papers. The one is this one by Lai et al., 2020. And they showed that it's actually 16 units of ethylene glycol in the chain that are the epitope that are recognized. And on the other hand, there is this very nice work from last year, Su et al., who showed with a number of really clever methods that there's a second type of anti-PEG antibody that targets both the end group and a segment of PEG. So the paratope is more complicated, and the epitope is also more complicated here. But for us, it boils down to the fact that the regularity of PEG, the chain structure, is the reason, this highly regular chain structure, why it can be recognized. And we should keep these 16 units in mind for what I'm going to tell you in the next couple of minutes. Alternatives, of course, we also know have been investigated and are intensely being developed. For instance, polyoxazoline, polysarcosine, and that's just a picture I gleaned from the first work here, familiar to some people in the audience because they are the authors. And that's alternatives. But then if you look at how many companies are specialized on producing extremely high quality pharma-grade PEG, on the one hand, it would be a shame to wholly abolish PEG. And on the other hand, of course, PEG is so highly established. So maybe we can find something in the area of polyethers. And that's what we are trying to do. So you see that's PEG, that's anti-PEG antibodies. And can't we isomerize PEG in order to obtain the type of structure we are showing at the bottom? If you take a close look, we've packed some of the methoxy structures in the side chains. Basically, we keep the ratio of carbons, oxygens, and hydrogen That kind of structure, can it be made? And of course, you could also consider it differently. If viruses escape our immune system by mutating, well, we could say let our polymers also escape the immune system by mutating them a little bit, even in a statistical sense. So they cannot be detected. Of course, we want to keep the length of the polymers for bioconjugation, for nanomedicine, very, very well controlled, obviously. But within the chain, if we vary the chain just a little bit by introducing a little bit of statistics, come back to that in a minute, that might be a way of avoiding immune recognition. And that's the way we do it. Copolymerization of ethylene oxide and the so-called glycidyl methyl ether, a really simple monomer. I should mention that the GME is not as simple as it looks. It's a little bit beastie. You have to really know how to tame it if you're a chemist, but it can be done. And then if you make these copolymers, of course, you're looking at, first of all, are these two units similar in reactivity? What about aqueous solubility? What about all the beneficial properties of PEG that we know very well? Can we retain them by performing this? And in the end, of course, cell compatibility, viability, and non-immunogenic character, which I put in the title, are the main questions that we want to address. So first of all, if you look at this copolymerization, there is one thing we really appreciate, and that is, if you look at those two monomers, and I should mention I'm teaching Organic Chemistry 101, really very basic. I'm teaching structural isomers in the second or third lecture to the students. Any copolymer with any composition is a structural isomer of polyethylene glycol. Yeah? And you see that if you look at the MALDI-TOF, that's a MALDI-TOF mass spectrum of a copolymer, and it looks like a MALDI-TOF of polyethylene glycol. Some of you may have seen that before. But this is a copolymer, I can assure you, with, in this case, 25% of these GME units. And so we can make all of these in, let's say, even, well, eventually pharma-grade quality. Not yet, we're not making them GMP. But you can make them with very narrow dispersity, since we only use the classical anionic ring opening polymerization, the very same method that is used to prepare pharma-grade PEGs by the many companies that provide PEGs all of us are using for conjugation and for nanomedicine. Dispersities are low. Interesting point is, if you look at the reactivity of both comonomers, there was a surprise for us actually some years ago when we started this work. We expected that EO should be more reactive than anything else. But what it boils down to is that both components disappear at the same rate. At the upper left, you see our online NMR experiments, and they are done in such a way that we look via NMR while making the polymer. We look at disappearance of both structures, and you see they disappear at the very, very same rate. Should mention we need thick-walled NMR tubes because we're working with EO at room temperature, boiling point 11 degrees C, but that can be done in NMR. And this means reactivity ratios are 1, which tells you it's a perfectly ideally random copolymer structure. And you can, of course, do simple statistics then. Even we can do it, although we're not a theory group. Some Monte Carlo simulation, what it looks like. And you see if you go to 50% GME, these 16 monomer unit containing blue PEG-type segments become less and less abundant. So that's the statistics you can do very easily. But you see if you go to 50%, well, probability is almost zero. Of course, it will never become exactly zero mathematically to find a segment of 16 EO or ethylene glycol segments in a row. So that's the way this works. Just on passing, I would like to note that, of course, leads to the fact that this is not crystalline anymore. Yeah? If you compare it with, let's say, 4%, that's top. In the middle, it's the red one is 8%, and eventually 15%, you see that the melting disappears because there is no packing possible anymore due to the statistics of the distribution of these sterically, well, not so demanding, but still demanding methoxy-methylene units in the side chains. Okay, let's come to some biological tests. First of all, marine spleen cell lines together with Matthias Broos at our university hospital in Mainz. And basically, the big red column is just to compare. That's a lipopolysaccharide, and the other columns are different concentrations of GME incorporated, not discussing which exactly is which, but you see basically there is no difference. It shows exactly the same effect as PEG, and we conclude that there is no stimulatory effect on immune cells compared to untreated, at least if you look at mice cells. If you look at human cells, that's work that's just happening right now. You see also, apart from, let's say, 2 outliers on the right side, if you look at T cells or B cells, there is not much of a big difference. We're still working on improving statistics further. But so far, we see that there is no toxicity of these rPEGs. By the way, we call them rPEGs. R stands for rando, because they are random copolymers, so rPEG is the abbreviation for rando. What I do not show is water solubility. If you have 50% of these GME units, since it is a structural isomer, you will still see that the polymers have a so-called cloud point, LCST, at 95 degrees centigrade, 94 to 95, so water solubility is very, very slightly less good than for polyethylene glycol, but it's approximately the same level. Okay, some competitive ELISAs, backbone-specific anti-PEG antibodies we bought. A comparison, and you see now we look at PEG, MPEG, GME, 16%, 24, 49%, different isomers with an increasing content of these glycidyl methyl ether units. And you see that if you go to 49%, we in these ELISA tests do not see any binding anymore for the backbone-specific anti-PEG antibodies. And of course, there are also the N-group specific. They are not really N-group specific. I showed you in the beginning they actually interact with a backbone, with one paratope, and they also interact with a methoxy N-group. And there is a little bit more of details you have to look into because it depends on how many ethylene glycol groups do you have directly adjacent to the N-group. And if you look at the one in the middle here, the structure, and that can all be made synthetically, so we can really design our PEGs in such a way to not interact. If you look in the middle, you see there is still binding because you have the methoxy group and then 3 units for the N-group specific antibodies. If you have only 2 units, there is no binding. So, because then after 2 units, there is this sterically demanding immediately group, this branch group in this place. So we know how to design our initiators. We cannot just use methoxide, but we have to really design an initiator with, let's say, 1 sterically demanding units to initiate these polymers. Let's come to the last part of this presentation. We've teamed up with the company Evonik. And Evonik is trying hard to, of course, become is already a top supplier of PEG lipids, which I don't have to explain here, because all of you know these structures. And okay, that's how PEG is made. And of course, we can replace PEG in PEG lipids by our rPEGs. That's what we've done. So we've used DMG PEG and ALC 059, both well known from Comirnaty and from the Moderna COVID vaccine. And well, at Evonik, then this PEG was replaced by rPEG at the lipid in those 2 structures. You see that's possible in a very clean way. That's also demonstrated by these MALDI-TOFs in the upper right, in the lower right corner. So that's very clean replacement. And these were then tested by various tests again ELISA. This shows, now I'm sorry, this is a typical industry type of slide. I'm not telling how much GME is in the different rPEGs because they don't want me to do that, but you can imagine from the slides I showed before. Anyhow, there are different rPEG lipids which differ a little bit in the amount of this second unit incorporated. And you see that if you compare the relative anti-PEG antibody affinity, we can really suppress this to at least a large extent. We don't know very clear yet whether the remaining small activity is just unspecific interaction or what happens. But clearly, what I showed you for the rPEG chains also is valid for these lipids. Similar encapsulation, of course, also encapsulation tests of mRNA have been carried out at Evonik. There's a ribogreen assay that has been performed, and also what we see here, and I think that's important, that we can achieve similar transfection efficiencies. So LNPs were made, and the only difference to the established LNPs is that we replaced the PEG lipids by rPEG lipids at Evonik. And you see there is, a nice transfection, so this appears to work. Of course, these are all, let's say, still explorative experiments. Come to one almost final slide. This is, you can of course not only use this in nanomedicine, you can also combine it, and that's a complete shift of direction. You can combine it with polylactide and then make materials. If you do this with PEG on the right side, this material looks like this. On the left side, if you do it with the rPEGs, they are highly flexible. You can make all kinds of shapes and structures which might be interesting for controlled drug release. So that's the final slide. 3 hypotheses, if I have 30 minutes of the coffee break maybe. First one, we are trying to generalize, but maybe it's not a bad idea not to use highly precise polymers for bioconjugation, but maybe use well-defined random copolymers because the immune system, in this case, will not be able to develop antibodies, to elicit antibodies. We like very much the topic of polymer sequence statistics. We think it's important at the biological interface, as I've shown. And in the end, I'm claiming, that's a point for discussion, that we can retain the advantageous property profile, but offer some additional, possibly, benefits. Well, thanks for having me, and thanks for listening.
Thanks.